Hello students, today we are going to study queuing theory, which is one of the chapter in operational research. So in day-to-day life, we are forming queues in so many situations. In cinema theater, in temple, to poll the vote. In so many situations, we are forming queue. So first, we should know what is mean by queuing system. So a queuing system can be described as a composed of customers arriving for a service, waiting for a service if it is not immediate, and if having waited for service, leaving the system after being served. So this is basic definition for queuing system, which is explained in this pictorial representation. So customers are arriving in this way and they are forming queue. After that they enter into server. After getting service, they are leaving out of the queue. So this is the queuing system. Basically we should know some important terms which are involved in queuing system in exam point of view. So first one is balked. So what is mean by this balked means if a customer decides not to enter the queue because of its huge length. So the length of the queue is very huge, then the customer decides not to enter the queue, then that situation is known as balked. And another one, on the other hand, a customer may enter the queue but after some time loses patience and decides to leave. So initially he enters, but after some time he leaves the queue because of that huge thing. That situation is known as reneged. And then another one, when there are two or more parallel queues. So if servers are more than one, we can have parallel queues also. So in that situation, the customer may move from one queue to another. So he is standing in one queue and moving to another queue for his personal economic gains. That situation is known as jockey for position. So these things are mainly asked in exam point. And then we should know what are the queue disciplines commonly used. So the main common discipline is first come first served. That is who is coming first to the curve is going to be served first. So otherwise it is known as first in first out. The another most commonly used queue discipline is last in first out. That is who entered the last in the queue is going to be served first. So that discipline is also followed in some situation. And another one is selection of service in random order. So the service is going to be done by random order. So these are all mainly used queue disciplines. So initially there are so many types of queuing model. So we are going to deal with this first type, that is MM1 queuing model. So in this queuing theory we should know so many definitions or notations. First one is arrival process. That is the customers are arriving in the queue. So that process is usually follows Poisson distribution. So in probability that Poisson distribution is a discrete distribution which has countably infinite or finite number of customers. So here also arrival process follows Poisson distribution. And then next one is queuing configuration, which is taken as a single waiting line with unlimited space. So that is our queuing configuration. And then queue discipline. So what is the queue discipline we are going to assume here is first come first serve, and service processes assumed as exponential distribution. And queuing model, so there are two types of model. One is a single server and another one is multiple server. And usually queuing models are represented in this notation, which is in general mentioned as A, B, C, colon, D, E. There this first symbol A denotes arrival rate, and the second symbol B denotes service rate, and the third one C denotes number of servers. So how many servers are in that system. And D denotes queue length, and E is population. So who are all going to benefit in that queue. So that is our last notation. So our first model is MM1 infinite. So this first symbol M is arrival rate, second symbol is all denotes service rate, and 1. So this one is number of servers. So we are going to have a single server. And then this fourth symbol denotes queue length. So our queue length is infinite. And then population is also here considered as infinite. And to solve these kind of problems, we should know the following terminologies. So first one is arrival rate. So we know arrival rate follows Poisson distribution, and arrival rate is usually denoted by the symbol lambda. And then service rate. So service rate follows exponential distribution and is denoted by mu. So this is our first model diagrammatic representation. So customers are arriving in this way, and they are forming queue in this line. After standing in queue, a customer is enter into the system, and after getting service, he is going to leave the queue. So this is the representation of this first model. So what are all terms we are going to find using this queuing theories? So many items we can find. So one is length of the queue, that is how many members are in one queue, and length of system. So system is nothing but number of persons in the queue and number of persons in the server. So here it is single server, so obviously in a time only one customer is in the server. So length of system is nothing but number of customers in the queue plus 1. So this is for this model. And we can find the waiting time in queue. So how many times we have to wait in your queue, that is easily answerable under this problem. And waiting time in system. So previously I told no, system includes queue plus server. So how many time he has to wait in the queue and service time. So together we have waiting time in the system. So all those things we can calculate. And then this notation is very essential, which is known as probability that the channel is busy. Otherwise we can call it as traffic intensity. In some book they denote traffic intensity by the symbol rho. Okay, so this is rho. So what is the formula for rho is ratio of lambda and mu. So we know lambda is arrival rate and mu is service rate. So ratio of these two things is our rho, and we are going to find these things under this category. So these are all formulas. So there are a lot of effort to derive all those formulas, so that things are not necessary for us. So we are going to consider only these formulae. So these are all essential formulae to solve problems in this model. So first formula is average number of customer in this system. So system means Q plus service time. So together is known as average number of customer in the system, so which is denoted by the letter LS. That is, L denotes length, so length of the system. So we are going to find that one. So formula for that one is lambda by mu minus lambda. That is actual formula. So we are taking mu outside, then this term becomes 1 minus lambda by mu. So we know lambda by mu is rho, so this term becomes rho by 1 minus rho. So this is formula to find length of the system. Either we can use this one, otherwise we can use this term also. And then next formula is average number of customers in Q, that is length of the Q. So which is lambda squared by mu into mu minus lambda. As usual, taking mu from this term, you get it is lambda squared by mu squared, 1 minus lambda by mu. So lambda by mu is replaced by rho. So we have rho squared by 1 minus rho. So we know rho by 1 minus rho is L of S. So this is splitted into rho by 1 minus rho into rho. So which is Ls into rho. And then we can find waiting time in system. So that is sometimes we are waiting in the queue and we entered into the server and the service is finished for us. Afterwards we are leaving the system. So that all time together is known as waiting time in system, which is denoted as WS. So what is formula for this one is LS by lambda. So previously we calculated LS, that is length of system. So that one is divided by lambda, then you get WS, that is waiting time in system. And then we can find waiting time in Q, which is denoted by WQ. So as usual, it is LQ by lambda. And then this factor is also essential. So what is the thing is probability for no customer in the system. So that a system has no customer, that means the queue is empty. So probability that the queue is empty, so that probability is calculated using this notation. So it is P 0, that is the system has no customer, so P naught, P0, so which is we know probability that the channel is busy is rho. Now the channel is empty, so we have only two possibilities. One is busy, otherwise not busy. So total probability will be 1. So we get not busy value will be 1 minus rho. So this is formula for probability for no customers in the system. And next one is probability for n customers in the service system. So at a time n customers are available in the system, we want a probability of that situation. So we can use this formula. So it is Pn. So notation is used here as P n, okay, because we are going to have n customers in system. So it is pn. Formula for that one is 1 minus rho into rho power n, okay. So this is rho and this is p, so you should differentiate both, okay. So we know 1 minus rho is nothing but p naught, so it is rho power n into p naught. So this is formula to find probability for n customers in system, okay. So these are all main terminologies or main formulae we are going to use in this method, okay. So using this we are going to solve this problem, okay. So our problem is a TV repairman finds that the time spent on his jobs has an exponential distribution with mean 30 minutes, okay. So we one repairman is there. He is going to spend to repair one TV set within 30 minutes. So within 30 minutes he can repair only one set, okay. So that is the data given here. If he repairs sets in the order in which they came in, okay. So what is the methodology he is used means the order in which the sets are coming in to the system, he is repairing those things. So that is indirectly they are saying who is coming first, being served first. So it is first in, first out, that Q discipline follows. And here server is repairman, so only one repairman is there, therefore server is one single server only, okay. So all those things we should know before solving one problem, okay, because there are variety of problems under these queuing system. We have multi-server, single server, and then limited customer. So we should differentiate all those things under various model, okay. So we are mainly considering first model, that is very important thing, okay. And what is the next one? And if the arrival of sets is approximately Poisson with an average rate of 10 per 8-hour day, okay. So what is given here? Arrival rate of sets follows Poisson. So we know arrival is always following Poisson distribution. So what is the average rate of arrival? It is given per day. So what is his per day? 8 hours, because he is going to work only 8 hours in a day. So 8 hours working is his one day, okay. That is his working day. So in that working day, in one working day, how many sets are expected to arrive is 10 sets. So it is given here, okay. So what are the questions we are going to answer? So what is repairman's expected idle time each day? So in one day, what is repairman's idle time? So idle time means he is going to not in busy conditions, so that is in idle position he is going to be. So what is the repairman's idle time? We are going to calculate in each day. So in one day, how many times he is not going to have idle manner, that is he is not having any work. That means our system is empty, because he is simply sitting and without doing any work. Ideally he is there. So we have to find how many times he is in idle condition. So that is our system is empty. So that idea we are going to find here. Afterwards the another one is how many jobs are ahead of the average set just brought in, okay. So now one set is arrived into his shop. So we have to tell before the set how many sets are available in his shop. That is, you have to tell number of sets in the system, because some sets are waiting in the queue and one set is in server. So totally we have to tell number of customers in the system. So these two things we are going to answer. So I hope everybody understood it clearly. So how we are going to solve? So first we should go with this rough work column. Okay, so here working hour is 8 hour per day, so that is considered as working hours. So first service time is given here, so we are taking service time. So it is given to repair one set he needs 30 minutes. Okay, so I selected that one. So one set he needs 30 minutes. So the another information is per day, isn't it? So arrival is per day and this one is minutes. So we should convert these two into same unit, either to minutes or to day. So that is very very important. Same unit both should available, then only we can solve our problem. So here this is in minutes, another one is in day, so we are going to change. So first we are considering one set is given as 30 minutes. So I am going to change this one into hour. So 1 hour has 60 minutes. So both side we are multiplying by 2. So 2 sets 60 minutes, which is 1 hour. That is 1 hour he can repair 2 sets. But he is going to work only 8 hours. So 8 hours is his working day, one day. Okay. So we have to calculate this one for 8 hours. So 1 hour 2 sets. So 8 hours obviously 2 into 8 sets, totally 16 sets, which is his one working day. So in one working day he can repair 16 sets. Okay, so this is service time, because he is giving service for repaired sets. Okay, and then we have to concentrate on arrival. So it is given in 8 hour day, that is his working day. How many arriving? It is 10 sets are arriving. So 8 hour day, 10 sets are arrived. 8 hour day is nothing but one working day. So in one day 10 sets are arrived. So now this is arrival is in day. Similarly service also in day. So both terms are converted into same unit, namely day. So this is very very important. Both unit both must be in same unit. Okay, so after calculating these things you come to main part. So it is given arrival rate. So we know arrival rate is denoted by lambda. So what we calculate arrival? 10 sets per day. Okay, so arrival rate lambda is 10 sets per day. And then service rate, which is denoted by mu. So we know service is 16 sets per day. And then first we should calculate this row. It's very useful because all the formulas involved this row only. So we are calculating row. We know row is ratio of lambda and mu. So it is 10 by 16. So which is 0.625 by calculation. And so first what we are going to answer, what is repairman's expected idle time each day? That means the repairman is in idle position, that is he has no work to do. That means the shop is empty, that is the system is empty. So we have to tell probability that the system is empty. We know probability that the system is empty is denoted by rho naught, P naught, which is 1 minus rho. So we have to apply that formula. So 1 minus row value is this one. So it is 0.375. So this is probability that the system is empty. But we want in one day how many times he is in idle condition. So we have to find that idle time. So expected idle time per day, which is number of working hours into P naught. So totally he is going to work 8 hours and P naught value is 0.375. So multiplying we get this idle time per day is approximately equal to 3 hours. So in 8 hour day he is going to be in idle condition for 3 hours. And then next we are going to calculate how many jobs are ahead of the average set just brought in. Okay, so earlier I discussed, for this we have to find the number of customers in this system. Okay, so that number of sets are ahead of the set just brought in. Okay, so number of customers in the system is denoted by LS, which is by formula row by 1 minus row. After calculation we get this is 5 divided by 3, so it is approximately equal to 2. So 2 jobs, so 2 jobs are ahead. So in the system 2 jobs are ahead. That means in the queue one set is there, because in shop they have 2 sets. So one is in server and another one is in queue. So that is we can tell the another one also, number of sets in the queue is 1 set. That is also we can tell. So so this is the basic model in queuing theory. So one by one we can solve more problems under this category. Okay, thank you.